Greetings, geologists, and welcome back for the life history of the Cenozoic. So there's so many animals we can talk about, so what I tried to do was lay out a framework in which we went through each epoch of the Cenozoic through the Pleistocene. I'm not going to address the Holocene except in one area, which is modern hominids, and we'll discuss that when we get to the hominids section. So up front, I need to tell you I didn't include the hominids in this section, meaning our ancestors as humans. I addressed some of the primate stuff, so we'll do more of that when we get to hominids. But let me caution you that students sometimes get confused because they're like, well, I thought deer appeared in XYZ, or I thought that all grazing animals came about in like the Eocene. You must realize that there was a progressive amount of evolution, convergent, divergent, parallel evolution occurring throughout the Cenozoic all over the world. And so animals evolve, and there's some groups that are distinctive to certain epochs. So I tried to name animals by name and teach you about some of the highlights of the important life forms. And this in no way captures anywhere close to all of the critical life forms. I mean, we could spend a whole semester on just looking at several of these categories. So let's get busy and learn about what happened in the Cenozoic. So when we're thinking about the Cenozoic and we look at life forms, we can kind of divide it by the Paleogene, Neogene, and the Quaternary. And I really believe that when the International Commission on Stratigraphy decided to pretty much disembark the name tertiary, this was one of the reasons why. Because in each epoch, unique things happen, and I think you can kind of divide some of the major radiation of mammals to the Paleogene, and then we see expansion of mammals and habitats that they lived in the Neogene, and the Pleistocene, in particular the Quaternary, represents the last ice age. And then we get to the Holocene, which is the most current, and we have basically some of the same life forms that we had in the last ice age. So in the Paleocene epoch, as we're starting over after the mass extinction event of the Cretaceous Paleogene marker there, known as the KT boundary prior to tertiary being eliminated as a term. But this marker is important because depending on where you are, the flora is different, and flora is important to giving us a clue as to what the paleo environment would be like. So if you can imagine western interior rocks, like let's say in Arizona and Utah and Nebraska, had warm subtropical conditions and plants such as this palm leaf, you would understand that this was a really interesting time, subtropical area. If you went a little bit further south, like you went down truly to Arizona and Colorado, you would find that it was very much tropical rainforest type area. So what I'm getting at is plant life was different, so was the animal life. It was a warm recovery after the Cretaceous mass extinction event. In the Paleocene epoch, our mammals were small. Keep in mind, mammals have been around since the Cretaceous period, through the Jurassic, and even through the Triassic, right? But we had smaller mammals that had survived the mass extinction event at the end of the Cretaceous period. So we're going to see things like rodents for the most part, and when you consider that rodents make up most of the population, when you look at percentage-wise of our kingdom Animalia in terms of mammals, it's almost humbling. So if you read your book, you probably got a stunning percentage of what amount of mammals rodents make up, and you take a new look at them with a different eye, right? A couple of key things I might point out. We know that fossil evidence strongly points towards primates evolving during the Paleocene. Now, there is some fossil evidence that suggests they appeared in the Cretaceous, but until that has been fully proven, we can put them as a marker in Paleocene. Some really important changes to primates are going to happen throughout multiple epochs of the Cenozoic. So understand that we're just beginning an evolutionary process that's going to divide and diverge in multiple different ways. We got a number of many of our first birds during the Paleocene, such as owls and ducks and penguins and vultures. And that's important to note because throughout the Cenozoic, we're going to pretty much end up with modern orders of birds that you would recognize in just a couple of epochs. When we think about the Paleocene, I really want you to think about what could have filled the niches of non-avian dinosaurs. So we started the Paleocene at 66 million years, and within 10 million years at the conclusion of the Paleocene, we had a remarkably different animal set of life forms. We had insectivore type mammals, we had rodent-like mammals, we had our first medium-sized forest-dwelling animals, we had large browsing animals, just a handful, I might add, and then our first carnivores. So some neat stuff evolving. Here's one of those carnivores. Gastenorus is a flightless bird, scary indeed. This guy got up almost pushing 6.5, little over feet tall, with a complete theropod build. If you look at this thing and be like, wow, that looks like a theropod. So you're looking at a full-fledged sized ostrich animal, and it didn't have flight, but this would have been a predator. There's some versions of these birds referred to as terror birds in terms of different species of these large flightless birds. So they existed for a long period of time. They didn't just come in the Paleocene, but I'm telling you this particular one did. So these would have been feeding on small mammals and whatever it could live on at that time. Dinocerata was a plant-eating rhinoceros. Believe it or not, bless his heart. You have to love him. He's so very interesting face. And if you look at him, you're like, wow, improvement for the rhinos over the years. Now, this is a rhino-like animal, and it lived from the Paleocene in where it first appeared and went extinct in the Eocene. So they were very large animals for their time. But they're going to feed on the changing climate fauna, meaning flora that's out there, plants, and be able to survive in that environment. Creodonts are our first carnivorous types of mammals that we're certain that really are, that evolved during the Cretaceous. They lived from the Paleocene and went through the Miocene epochs, and then they pretty much go extinct. They used to be considered the ancestors of modern carnivores, but meaning they were thought to give rise to something like canines, but nevertheless we know that they're not. So these are carnivorous animals for sure, but they are not the direct lineage to them. Myostids, however, are. These are an extinct group of carnivores that gave rise to cats, dogs, bears, and skunks. So you would expect to have seen them, even things like mongooses, hyenas, and other felines and canine-related friends and families of these particular guys. So these were the guys that were the extinct ancestor group to what you would think of as carnivores today. So we can't have a conversation about the Eocene and its impact on climate without talking about the PETM. So what does the PETM stand for? Paleocene, Eocene, Thermal Maximum. I often ask this question on tests, and I'll say, when did the PETM start? And I almost get every time Paleocene. It really didn't start till 55.8 million years ago. It really puts it in the Eocene time frame, because you're looking at 66 to 56 million years for the Paleocene. It's at that boundary marker. That's the bottom line. A majority of this particular event was an Eocene event. It happened at the very beginning of the Eocene. And it wasn't a very long event, but nevertheless, here's what's happened. We changed the climate very fast, and we'll talk about one of the reasons it happened in just a second. But what you need to know is that we had the highest mean average world temperature from the Cenozoic era during this time. And it impacted plants and animals substantially. So it's a scary thing, because from pole to pole these temperature ranges change. That makes the PETM a very good case study for what could happen with carbon concentrations in our current day atmosphere. So you have to imagine there was 1,000 parts per million by volume in the atmosphere during PETMs. How can we verify that? Through deep sea sediments. And we can't do it through ice cores because we don't have ice cores that date that far back. So typically it's deep sea cores that we look at for this information. About now, we sit around 360 to 390 parts per million by volume. So you're like, we're a long way from 1,000. Well, I'll let you in on a short secret. Basically, for every degree of climate change increase that we see in Celsius, it means we double that carbon number from the pre-industrial revolution number, which is right around the 290-ish to 95-ish range. And so what you're looking at is a bad thing, because every time we go up a degree, our carbon has doubled. And so we are monitoring the atmosphere for that very reason, so you can have a good feel and understanding that this is a long-term problem, and the PETM can give us that information. One of the things that happened in the PETM was it's thought that methane clathrates, which is just a fancy term for an ice fabric that builds at the bottom of the ocean. It's kind of like a lattice or a cover that covers a methane pocket. And when that ice melts, it releases a bunch of methane all at once, which escapes from the ocean up into the atmosphere. And methane is substantially holds more heat than carbon does, so it makes it a very important greenhouse gas. When this occurred, this event where these methane clathrates melted, it caused a die-off of deep-sea marine benthic foraminifera, one of the most noticeable in the rock record since the Cretaceous mass extinction event, which I might add correlates to some of our oil and gas. So I do want to say that that's a good thing, but it's not a good thing when you think about what happened to the life in the PETM. The life got smaller in terms of mammalian size, and certain plants could exist like beans, for example. So a drier climate, not all areas would be completely arid by any stretch of the imagination, but enough to impact life forms for several 100,000 years. When we think about the Eocene, after the PETM recovery, and as an FYI, you're looking at least 100,000 years for a major cycle change with the climate to really recover from major global warming like we saw in the PETM. So in the early Eocene, we had the oldest known fossil of the most modern orders of mammals, and they're going to radiate greatly after the PETM. Now, most mammals were very tiny, under 10 kilograms, which is going to be over 20 pounds, just to kind of give you flavor. Artiodactyls and Perissodactyls were the two that really originated during the Eocene and produced some of the most important groups that we'll be looking at. So I need to let you know that the Perissodactyls are going to be the more common back in the Paleocene period, but now in the Quaternary period, Artiodactyls are much, much more common. Perissodactyls are your odd-toed ungulates, which are hoofed animals per se. So they either walked on one or three toes, essentially is what happened. And we'll be looking at various different types of them. There was rhinoceroses, tapirs, extinct horses. And nevertheless, these were very common back in the Paleogene period and much less common today. As a matter of fact, we only have 17 living species as in the current time. So they went from being the dominant to the least dominant. Totally different with the Artiodactyl. They were much less common in the Paleogene period and became much more common in current time. So a lot of these Perissodactyls went extinct at the end of the Eocene or Oligocene, and they are some very famous guys along the way. The Hyracotherium is one of my favorites. This is the largest known mammal herbivore ever found on the planet. Now, I'd like you to imagine during the Eocene that this rhinoceros-like animal, it was hornless too, got up to the size of 4 African elephants. I mean, he is huge. This guy fed at the top of trees. I mean, we're talking like this guy's 18 feet tall at the shoulders. He is whopping 20 tons and 26 feet long. So he's like a giant school bus. He's really quite impressive. Now, he browsed on the leaves. We think of branches and trees, the way his morphology of his bones were, and he was busy eating on those things until he went extinct. So he lived in the forest of Asia from 34 to 23 million years ago. The Hyracotherium is one of the most famous of the Eocene animals, otherwise known as Eohippus. Eohippus means dawn horse, which is important because it's the dawn of the equestrian family that most of you love and know as horses. So Eohippus, I'm not kidding you, is the size of a small dog or a very, very large house cat. So I'm going to tell you, if you could think of just maybe a poodle or a little larger, that's what this guy was like. Tiny little horse, adorable actually. They had 4 hooked toes on their front feet and 3 hooked toes on their back feet. They had little pads on their feet, so they would run around in the forest looking for leaves and plants that they would eat. And they're the very beginning of the horse family. So literally in each epoch, we have a new graduation in terms of horses where they kind of change their morphology. They grow in stature, their teeth change. That's a real important part of the horse story. Their skulls change, and even the size of their brains change. But this was the very first one, made its debut in the Eocene. What is an artiodactyl? Well, they're even-toed, cloven-hoofed, which means they walk on 2 toes. Now, you would know these as things like camels, cows, deer, pigs, sheep, goats, giraffes, antelopes. These are just a few of your artiodactyls. So these organisms became very widespread and adapted to a wide variety of habitats once grasslands became more prevalent during the Oligocene and certainly by the Miocene. But even in the Eocene, we saw a rapid evolution of artiodactyls to fill these niches. Artiodactyls got reclassed as order Sotartiodactyl. This change is really important. Here's why. It includes the whales. So this is a fairly new development. Like when I took historical, there's no such thing as that being included here, but it certainly is now, and we'll learn a little bit about some of those animals here shortly. So whales and dolphins fill in this category as well. You might be going, okay, I thought they were marine animals. Yes, but there's more to the story. Nevertheless, artiodactyls are the even-toed ungulates. So cloven hoof simply means they walked on 2 toes. The entelodont is an animal from the Eocene that I think that we should talk about. This was an extinct family of some of the most scary pigs-like animals you've ever seen. They're omnivores, they definitely carnivorous, but also ate vegetation, probably seeds and fruits, whatever they could get their mouths on. But these guys are huge. Sometimes they are referred to as killer pigs. I've heard them called a lot of things. But they no doubt were scary. So you would have seen these in North America. That's not a fun thing to go back to in the Eocene all the way through the early Miocene. They lived in plains and forests, and they were definitely apex predators of their time frame. So imagine a wild pig that's 7 feet tall and weighed up to a little under half a ton. He's impressive, and these guys are pretty common in terms of Eocene fossils. Ambulocetus is the next animal, which is one of those that we were going to talk about with whales. This is an early Eocene whale that still had limbs that would allow it to maneuver on land. So that's kind of an important evolutionary jump. Remember, it's an artiodactyl, right? Well, it's been reclassed, so make sure you know that. But nevertheless, this animal could still have the bone structure it needed to maneuver on land. You're looking at it right here in terms of, see this material that actually still had 4 limbs, and that's important. Basilosaurus was a late Eocene whale that had vestigial rear limbs. What does that mean? It basically means they were remnants of what used to be there. So we've gone from having these really big noticeable limbs from your whales of the early Eocene to basically not having that in the late Eocene. What other mammals were important to the Eocene epochs? I think this is a pretty important one. Dogs made their debut by the Middle Eocene. So if you have a pet dog, you can go, oh, you're an Eocene animal. Bats first appeared. Now you may think, who really cares about bats? They are so fascinating. They are really interesting mammals. And they started having fossils, and that's what you're looking at in this picture, as far back as Eocene. Deer, antelope, early camels, and giraffes made their debut during the Eocene. Anthropoids made their debut in the Eocene. Prosimians are the lineage in which this came about during the late Eocene. I think this is a really important thing to connect the dots, that these animals are going to kind of radiate and diverge, and ultimately the lineage will develop down the line in the Miocene that's going to lead to hominid. So we need to take careful note that this is one of the big diversions of primates that's going to happen. Fossils of these animals can be seen and found kind of southwest of Cairo, Egypt, and they're known for having distinctive types of features. So you have to imagine that this region of Egypt doesn't look like it does now back in the Eocene. Everything was warmer, greener, and a little bit more lush, right? So it would have been a tropical rainforest where these animals would have lived. We know that lots of the families of these types of organisms today live in those environments. Right now, we have found 20 species, actually more than that, of these guys in rocks from that area. Egyptopithecus was a anthropoid that had both monkey characteristics and features like apes. So it's one of those that kind of had on both sides of the fence. And it's a famous anthropoid that you need to know about. So we get to the Oligocene epoch. We have a climate shift. Now, we're still going to have, I'm not saying it's cold by any means, but we're going to have a shift. Sea level drops. The regression of the Tejas Sea is fully complete. We're going to lose some marine organisms during this regression, and we had a cooling trend that started to occur during this epoch. What happened was the climate got cooler and it got drier. So plants and animals are going to shift along with that and adjust evolutionary-wise to fit into these new niches, specifically what's going to start the grasslands era in terms of geologic reign for these mammals. Couple of things I think are noteworthy about the Oligocene epoch is, one is cats evolved during the early Oligocene. That's an important noteworthy thing, right? Hawks, eagles, falcons, a lot of your raptors appeared during this time. So birds continued to evolve and radiate, but we know by now we definitely had these organisms in place. Adiocetus is a type of whale that evolved by the Oligocene epoch, and by now we have both major types of whales. We have baleen whales, which are the ones that have plate-like teeth that are filter-type feeders that are going to feed on small phytoplankton or even krill, for example. And then we have our teeth whales, so they both evolved at this time. This particular whale had both attributes of the filter feeding teeth and then the real teeth. So it was kind of a unique animal, even had a blowhole at the top of its head in between the head and the snout area. The Brontotherium, one of my personal Oligocene favorites. This is a large rhinoceros-like animal. It was an herbivore of its time. An interesting story here. His name means thunder beast. So let me give you the background. The Sioux Native Americans associated this animal with thunderstorms. So if you understand where they live in South Dakota, that's not far from the Badlands, and these bones would appear after a rain event, likely to be washed out from fossil layers that were enriched with these, and So they associated thunderstorms with this and actually thought that this was an animal running across the sky. And so it fell out of the sky. They gave great care to the bones of these animals because they associated water resources with them. These guys were pretty big. They were up to 8 feet tall and 3.5 tons in size. But what's unique are these two appendages that come off of their nose. That's why I'm fascinated by them. That's just, wow. I mean, what happened with that experiment, right? But they're really cool. They're like my favorite Paleogene animal simply because they're neat. Eohippus ranks up there with it, but this one's pretty awesome. Hyenodon was not so nice. This would have been one preying on smaller animals that you'll learn about. This was a carnivorous mammal that existed all throughout North America in places like the Badlands. So it was just like very close to a modern day hyena, but it's just a different type of animal. Old world monkeys include macaques, proboscis, and then, of course, baboons. And so when you think about these animals, they have a definitive characteristic that makes them different from New World monkeys, including location. So one of the things I want you to know is their nostrils are close together and they're not far apart. So a couple of the characteristics were similar to New World monkeys. They had grasping hands and non-prehensile tails. Old World monkeys were characterized by nostrils that were close together, not far apart, had grasping hands and non-prehensile tails. What does that mean? Non-prehensile tails basically means they couldn't wrap. So if you have a prehensile tail, they could wrap around things. They are found in the tropical regions of Africa and Asia. So you're looking at Old World monkeys in these areas right here. So they are thought to evolve from a ancestor that we learned about earlier from the Oligocene Epoch, and they have radiated to these locations. So what's the difference between an old and a new world monkey? These include the howler monkeys, the spider monkeys, and the squirrel monkeys. And they have a more flat face, a widely separated nostril, not close together but widely, and they have a prehensile tail, so they could wrap their tail around stuff like trees. They only live currently in Central and South America and evolved in the early Oligocene. They likely came from African monkeys, so they're going to be these guys right in here. So when you look at the range of the two, you understand that monkeys may be worldwide, but they're in very distinctive habitats that are unique. This is a great time to take a break, geologists, so I'll see you back in a few minutes after you've had a chance to do that, and we'll learn about the rest of the Cenozoic mammals when we return. Bye!